So a Taylor polynomial is actually like a polynomial of best fit. So you can have a linear line of best fit, a quadratic best fit, a cubic best fit. But the idea is that you have an nth degree. So if it's linear, it's a first degree. If it's quadratic, it's a second degree. Cubic, it's a third degree. But you have different degrees of polynomials. So the way a Taylor polynomial works is that if f, your function has n derivatives at x equals c, so you're picking at a certain x value, and that's what we call where it's centered, then the polynomial p sub n, so the sixth degree Taylor polynomial would be p sub 6 of x equals f of c, and that's just the function value where you're actually centering it, plus the derivative at c times x minus c, plus the second derivative at c over 2 factorial times x minus c squared plus dot dot dot, and you'll see plus the nth derivative at x equals c over n factorial times x minus c to the nth. So this is called an nth degree Taylor polynomial. If you're centering it at x equals 0, so c equals 0, then it's called the nth degree Maclaurin polynomial. So this is after Brooke Taylor, an English mathematician, and then this is after another mathematician, Maclaurin. So when I said that this was like a line of best fit, if you look at this first piece here, f of c, that's just like a y value. So if we're Maclaurin, this would be your y-intercept, plus your derivative at c, that's your slope. So think Maclaurin for a minute. This would be like your b, your y-intercept, plus your m, and then x minus 0, because it's centered at 0, would be x. Y equals mx plus b. But then you go into something quadratic. If I wanted a quadratic line of best fit, because we're talking about different kinds of functions that have curves, so you can have different kinds of lines of best fit, lines and curves of best fit. So the real pattern that you'll see a lot is a little bit more than this. So if you take this piece right here and you use this at the very beginning, so what I have here is I have an f of c, just my original function, times x minus c to the 0th over 0 factorial, plus f prime of c times x minus c to the 1st over 1 factorial, plus the second derivative at c times x minus c to the 2nd over 2 factorial, plus, and I would go out for a while until I get to the whatever degree I need, like the 3rd degree, the 4th degree, etc., and then I would stop. And it is a polynomial, so there is a stopping place. Later when we do Taylor series, you'll see that they actually keep going forever, but the polynomials do not. But what I want you to see are the numbers here. So it's the first derivative, it's x minus c to the 1st over a 1 factorial. A second derivative, x minus c squared over 2 factorial. This is the original function, so there's no derivative there. X minus c to the 0th, well, we know anything to the 0th power is 1, so this would just be an f of c divided by 0 factorial, and this is by definition, but 0 factorial equals 1. So this, following the same pattern as these, is just your f of c, so it follows. But what I want to emphasize is that if I stop right here, that is the linear, or the linear approximation for your polynomial, your quadratic approximation for the polynomial, and you can go from there. So we'll actually find some Taylor polynomials on the next videos.